This is Kevin from Performance Trends. We're going to talk about a compression ratio calculator today. I'm going to start up the program here. And it comes in three versions, Standard, Plus, and Pro. It's got these little introductory tip messages. You can, if you've read them and understand, you can click here and you won't have to see it again. Or if you just tap the Enter key, it's the same as clicking on OK, and you can get through them. The compression ratio program obviously will calculate compression ratio, plus a bunch of other things like dynamic compression ratio, cranking pressure here, bore stroke ratio, rod stroke ratio, and such. It has different options for how much detail you want to get into. For example, typically when you first get the program, it'll be in the simplest version here, just the bare basics to calculate compression ratio. And you can see you can turn on more details here. Most people go automatically to the most detailed inputs they can get. So rather than filling all this stuff out, I'm going to just open an example. And you can do this too. Once you'll fill up this screen with several examples. You can save your data and print it out again, open it up, and recalculate things again. So now we've populated all this. And you'll notice here that if we click on the different inputs here, we have a definition here, or these outputs here, these calculated outputs. The definition is given down here. Now there's two basic functions when you ask for the most detailed inputs. There is calculating compression ratio, and there's also this rod length stack up or deck height stack up, where you have rod length, deck height, piston compression height here, and where is it? Deck height clearance, right here. And you can see it's going to check to always make sure that they add up to giving you the correct deck height clearance. For example, if we change a piston compression height, I mean from 1.33 to 1.3, got to press enter so it knows you're done changing things here. It's going to give you a little explanation of what it's going to do. And you can see the deck height clearance has now been adjusted to make sure these four numbers always add up to what they should. Now let's see here. We got a 9.57 compression ratio. Let's see here. No dynamic compression ratio. Why is that? Oh, I didn't click on the one with dynamic compression ratio. Okay. The dynamic compression ratio is 7.38. It'll be less because, first off here, let me do this. I just hit the maximize button. You can see it. Everything got adjusted to fill the screen. So you can see if you got old eyes like me, it's a lot easier to work with. Dynamic compression ratio has to do with the idea that compression ratio says, what is the compression ratio if the piston's at bottom dead center and compresses to top dead center? Dynamic compression ratio says, well, it doesn't really start compressing until the intake valve is closed. And it could be, up the bore quite a ways, depending on the intake valve closing. Now, this is not closing at 50 thou or something. This is when the valve actually sets on the seat. So here we have an intake valve closing of 69 degrees after bottom dead center. And you can see here, this little balloon here tells you what's going on here, and just like it does down here. What happens if it's really early intake valve closing, like a very conservative cam, like only 40 degrees? You can see the dynamic compression ratio goes way up. Now, some people believe a rule of thumb for dynamic compression was something around 8 is a good number. We let our engine analyzer programs deal with that because there's so many other things that go into what's the good compression ratio for a particular engine combination. But we give it here because people are used to seeing it. And again, here, cranking PSI with this dynamic compression ratio should be about 235 PSI. So anyway, so we got, let's say, I'm going to put this back to 69 where it was. And you can obviously just change anything you want, like these are the proportions, the contributions to compression ratio. That most of the compression ratio volume, the clearest volume up here at the top is coming from the chamber in the head. The gasket here, which is gasket thickness plus gasket bore diameter, is giving you how much contribution from the gasket. For example, if you go down to a 0.3 gasket, only now 7.7% is here. You can see the compression rate and dynamic compression ratio have increased. Here are the volumes for the engine, or for the cylinder anyway. I don't know how many cylinders are in this engine. Or do we? Yeah, we do. Number of cylinders here. A little more tech help. But yeah, we have number of cylinders, so we do know the complete engine volume also. So obviously you can change things here. If we go with, let's say we got a dome top on the piston, we can say how much cc's is in the dome. Let's say 5 cc's in the dome, and again you can see it draws a little bit of a dome there, and you can see that the compression rate has gone up again. You can also say you got a dish of 5 cc's, and it draws a little bit of a dish here, and you can see compression rates are now dropped. There's these calc buttons here. Calcs are little utilities that you can use to calculate something. Let's say from, let's see, this is from seeing a piston with it down in the bore a little ways. So you drop it down in the bore, and you got Smoky Unit came up with what they call the cavity plate. It's a plate you can put on the top of the deck here, and it's got a certain volume in it. You put the piston at TDC, fill it with fluid, and it'll tell you if it was 100 cc volume to start, and you can only get 88 cc's in it. It must be 12 cc's of volume from the dome. So anyway, but we're going to go with just a flat plate. Piston depth down the bore, let's say, is 200 thou, and the number of cc's we could put in was 20, and it says the dish cc's is minus 19.2, which means it's got a dome actually. If we could get in, let's say, 60 cc's, then it says the dish is 20.8. So you can just use that by cc'ing the piston here with a flat plate on it, flat plate, and the piston's down the bore 200 thou, or 2/10 of an inch. If you decide to use that, it will fill that in here for us. And you can see if we click on these various input also, you can see a little diagram here showing you what does this mean. Ring depth is from the top of the ring to the top of the piston and such. So there's a lot of good stuff in the program. And obviously you can, I've made some changes here. I'm going to click on Save As. And now instead of it's going to be this one, it's going to be Rev 2, Revision 2, let's say. And now you can see the name up here changed. This is a real handy option here also. Adjust specs to get a desired compression ratio. What happens is, let's say I want to get exactly a, let's say a 9:1 compression ratio. And it says, what do you want to do to get that? And I want to adjust the gasket thickness to get that. It says, what compression ratio do you want? I want 9. And it says it's going to require a negative gasket thickness, which is not possible. So let's say we try it again, but now we're going to adjust the cc's in the head. I want a 9:1 compression, and it says with this chamber cc 67.5, I am going to get didn't work. What happened here? Adjust the cc's. We want to do a 9. Oh, I'm sorry. There it is, right there. And you can see 9:1 compression from a 54.65 cc's in the head. So you can see there's a lot of real handy things that can be done with the program. It is probably one of our more popular programs for engine builders. Most engine builders, once they get this, they'll never go back to doing it the old-fashioned way with a calculator, because it really does ensure you're not making dumb mistakes. You're going to get a good compression ratio. Obviously, you can print this out and give it to a customer to see that you've covered all your bases. You check the compression ratio, and it just is a real professional look, handing a customer a nice printout. Thank you.